The module for alkynes has two classes, 19 and 20. There's already a video for class 19, study sheet. It looks like that. And it's one reaction, but it's a reaction that you need to know well because you need to know the mechanism. And you need to understand this idea that your alkyl halide has to be primary or a methyl halide, or else you will not get this. People think of this as addition, but actually it's substitution. You're substituting out the bromine for all of this, and you're connecting that with a dot. That has to be primary or methyl. Class 20 are a lot of reactions, but most of them you don't need to know the mechanism for them. Let's take a look at class or reaction 20A first. We're going to make an alkyne from an alkene. In a previous class, you learned how to make an alkane into an alkene, and now we're going to go from an alkene to an alkyne, or make the alkyne from an alkene. The alkene that I want to demonstrate this on is this one here. It doesn't matter if it's cis or trans. Let's do something like, something like that. Like that. It's a two-reaction process. Someone in class, one of the classes asked, in a synthesis, do we have to break up the two reactions? Do we have to do reaction 1 first and show the product, and then do reaction 2? If I teach it as a pairing, for instance, the pairing here is Br2 and then a strong base, NaNH2. If I teach it as a pairing, you are allowed to keep it as a pair and draw the product after the second reaction. If you don't understand what I'm talking about, you will when you get to synthesis. Synthesis is you line up maybe 4 or 5 reactions in a row, but you have to show the product at each reaction. He was wondering if you could pair the reactions together and not have to show the intermediate product, which is fine. Anyway. What I notice here is that this carbon and this carbon, I'm going to try to make a triple bond between those two carbons. I notice that both carbons have a hydrogen. That's essential if you start with an alkene. Because we need to make space, eventually your product is going to look like this. Triple bond, there's your dot. There's your triple bond, and here's your second dot. And then just count carbons. Black, black, and then 2 methyls. In lab, I think you're learning how to draw alkynes properly. It's typically the atoms next to the triple bond. They're all in a line. So look at these 4. Those 4. That's linear. Okay. If you make an angle, I don't know if I'll take off points, but it just looks weird, and it's going to... Sometimes when it looks weird, you either don't trust your answer or you change a good answer to a bad answer. So what is happening here? This one, again, I'm not going to show the full mechanism, but let me show you the parts. So this is how. You have your alkene, and you have Br2. By the way, you could also have solvent. So I'll put these in parentheses. CH2Cl2, solvent. Okay. You don't have to put it, and sometimes I don't put it myself. Okay, oops. And so here, I'll put the solvent. another chlorinated solvent is CHCl3, that's fine. And you get this dihalide. Count carbons. When we do the next reaction, which is a double elimination, remember how I drew these two hydrogens? Well, those two hydrogens are going to be very important. We have the hydrogen here, and okay, and a hydrogen here. And see my two dots? You're always trying to make the triple bond between the two dots. Sometimes you can't. If you don't have hydrogens on those dots, you won't be able to do it. So the second reaction is with NaNH2, and you're actually using it twice. Again, I'm not showing you the mechanism, but in the first elimination, let's say I remove, it doesn't matter which bromine, but I'll remove the bromine all the way on the left. That means you have to remove the hydrogen on the other carbon. So look at what I have on my two dots now. Dot here, dot here. What went missing? The Br and the H. But which H? The one on the beta carbon. So I still have this hydrogen here. As a reminder, if I want to remove this bromine here at the alpha, I have to remove a hydrogen on the beta. Again, there's mechanism, but I'm not showing it. It's either gonna be too cluttered, or I just want to stay consistent. You work on the mechanism at home. What if I want to remove the other bromine? So that becomes a new alpha, and now I have a new beta. And I am trying to make the triple bond between the two carbons. That's a second serving of base. And we have this now. See, now both carbons that were blue dots now have no hydrogens. I needed both of those hydrogens to do the elimination, the double elimination. Let me write here, you need to know the mechanism for the elimination. And let me make it very clear. M here, M here. Okay. No mechanism. For the double elimination. And if you really want to be specific, which I think you should, because it will help. What are you eliminating? The hydrogen. The beta hydrogen elimination. If I'm eliminating hydrogen twice, can you find those two hydrogens? It's these two. If you go way to the beginning, it's these two. Remove hydrogen twice. All right. let me draw you a molecule that will not be able to make me a triple bond. If I have this molecule here, alkene again, and let's say we have that. Okay. If I try to do the same process, Br2 with NaNH2, on the exam, you could write, or it would be multiple choice. One of the choices is you can't make a triple bond. Again, the only place you potentially could make a triple bond is between the dots, because that's where the bromines are going to go. But the answer here is that cannot. Cannot make, let me write this clearer. Cannot make triple bond. If you try, look how ridiculous this looks like. You know, at no point in any of our reactions do we get rid of carbon-carbon bonds. So I can't get rid of a methyl group, even if I want to. See that second blue dot? Well, aren't there 2 methyl groups there? Oh my goodness. That one. So this is not good. And if you do your accounting, only one of the double bond carbons has a hydrogen. You cannot make a triple bond. You are not expected to draw what you would make. You will make something, but you're not responsible for that. So you don't need to know. What is actually made. You're still going to do an elimination, but most likely you're going to eliminate maybe once between the dots and make another pi bond next door, because there's a hydrogen here, and you could have made a double bond here, but you don't need to know what it looks like, or you don't even need to think about it. You just need to know which alkenes are impossible to make the alkyne. That is reaction 20. That was a little bit longer than I expected. Let's see if we could fly through the rest. Okay, let's go to 20B. This is addition of HX. Okay. Yeah, we're gonna fly through this. It's good to have, for a lot of these examples, it's good to start with a terminal alkyne. And I will always write excess, just so you know you have to do this at least twice, or you're always going to do this twice. For instance, excess HCl. Markovnikov says you're going to put the chlorine on the more substituted carbon, and because it's excess, we're going to do it as many times as there are pi bonds. We have 2 pi bonds, and so we're going to do this 2 times. The first time we get a chlorine and a hydrogen. The hydrogen is on this carbon. So the first time, you'll still have a double bond here. Okay, let me do this a little bit more clearer. Your final product is this. Okay, your intermediate is this. Double bond chlorine. So that's after the first addition of HCl. After the second addition, you get that. Okay. Let me do an internal alkyne. It's not even symmetrical, okay? So, unfortunately, you can't decide which carbon to use. You're going to use both carbons. So this is a multiple choice problem, because I could ask you which product is not likely. Let me show you the 2 products that I think are made. Keep track of your 2 blue dots. And for one product, you have 2 chlorines on one of the carbons. Chlorine, chlorine. But because they are equally substituted, it's just as likely, honestly, to put it on the other blue dot. Chlorine, chlorine. Okay. And so I might show these two plus another two that are ridiculous, and you'll say no. This reaction can either will give me a mixture of this and this. There is no preference because they're equally substituted. Over here, the two blue dots are not equally substituted. Dot, 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 dot. Any questions about this addition of HX? No mechanism, but know the intermediate. KNOW, no. NO, mechanism. KNOW, intermediate, the one in green. Okay. Next, 20C. Oh no. We're not going to make it. Reaction 20C. Addition of X2. Addition of X2. Any triple bond, terminal or internal. I will say excess. I will give you the reagent. And now both carbons get 2 halogens because you're adding Cl twice. That's a total of 4. In lab, you're going to practice drawing a zigzag if it's alkane, linear if it's alkyne. You get tetrahalide. No mechanism. Heck, I'll even say no intermediate. Okay. That's 20C. Let's see. Okay, good. 20D, A, B, C, D, D, E, F. We have 3 more. These will go fast. D, E, and F. Okay, I know I was trying to make lists, but a roadmap for this is not too bad. It's only 3 roads. The first road is H2, PT. Put your 2 blue dots. It's an alkane, so make sure you zigzag everything. Zigzag like this. Okay, like that. Let me draw 2 arrows. And let me draw the 2 possible alkenes. So you start out the alkene horizontally like this. And in one version, your 2 groups are on the same side. For the other type of alkene, start out the same way. Put your 2 blue dots. And the 2 groups are on opposite sides. One's cis, one's trans. One's E, one's Z. Okay, and so you are expected to know these reagents. Cis, trans. The cis. What I remember with cis is that your hydrogens are also on the same side. How do we do that? Because you have hydrogen gas. The hydrogen gas adds at the same time the 2 hydrogens. You just can't forget, though, that there's also a metal. PT, PD, or nickel. Nope. If I do this, I will do that. Those are too strong. I need a weaker form of the metal. That's called Lindlar's catalyst. My bad. Lindlar's. You don't have to put a parentheses. Catalyst. Actually, I don't think people do that. And I think people don't put S. Okay. Lindlar catalyst. By the way, Lindlar catalyst is palladium. but it has some calcium carbonate to kind of weaken it. That's how to make the cis. To make the trans, it's kind of a weird combination. Sodium metal, so it's not plus sodium, it's actually neutral, so they put a little zero. With ammonia, which is normally a gas, but they make it liquefied. Don't ask me the mechanism for that. I have no idea. Well, I have a little bit of idea. But eventually the hydrogens will be on the opposite side as well. Okay. All right. One last thing, and then I gotta stop this video. That's reaction D, E, and F. If your alkyne is terminal, if your alkyne happens to be terminal like this, and you want to make it an alkene that looks like this, you could do either. You could do either, and it doesn't matter. You could use H2 with Lindlar, cat, for catalyst, or you could use Na metal with ammonia liquid. It will give you the same product. Because this is neither cis nor trans, but in all cases, you have to make the alkene. It's not going to be no reaction. There is going to be a reaction, and it'll make the alkene. In this class 20, there are 1, 2, 3, 4, 5, 6 reactions. The idea here is that you study the reactions by themselves, but eventually you need to know them so well that you could do synthesis. So know well enough to do synthesis. That will be a topic for another video. I just wanted to make a list for your reactions. All right, no questions. The video link will be posted as well as the PDFs.